Right, so we're trying out the first hybrid session of Priberam Lunch Seminar. So thank you everyone for coming here in person and also everyone at home. Today we have João Gante. He was also here last year. It was a really great talk, so we decided to welcome him again. He did his PhD here at Técnico in machine learning and artificial intelligence for telecommunications. And he's currently a machine learning engineer at Hugging Face, leading the generation team. Thank you, João. The floor is yours.
Thank you so much, and thank you for having you again. This is a new slide deck, so I'm not sure if it will fit this time, so let's see. The talk today is about essentially what happened in the last year with respect to open access large language models and to a smaller extent vision language models. And I want to start with a recap of what I talked last year, or what happened between 2023 and 2024. First of all, we realized that the chinchilla scaling laws are dead. So the chinchilla scaling laws are a set of scaling laws created by a team at DeepMind, where they essentially said that if you had a certain amount of compute, there was an optimal model size to be trained to squeeze the most of that compute. And what we concluded in the past few years is that it is good to break the chinchilla laws. So to have models that are smaller than what chinchilla laws would have predicted, but train them for longer. The models do train a little bit slower, but we use the models at inference time. Oh, that's not, lights are not changing. Okay, so let me, okay. It's not mirroring, it is. Maybe I want to share my entire screen instead. Okay. Is it good? Okay.
Thank you.
Sorry, folks at home. So these chinchilla laws, we have realized that it's good to break them. It's good to train the model for longer, because we train the model once, or we do a few training experiments, but we actually use the model at inference time many, many times. So the smaller the model is, the cheaper it is to use at inference time, and therefore people are happy to use smaller models. Second thing we realized in the past few years is that dataset filtering is good. So on one hand, you probably have heard many people saying that the data of the internet is over and we need more tokens to get better models. But at the same time, garbage in, garbage out. So it's good to filter our datasets. It's much better to create a smaller subset of the dataset and pass it more than once at model train time, because we have so many tokens that we don't do many epochs while training these large language models. This is one example of a high-quality filtered dataset that we have created at Hugging Face, but there are others nowadays. There were also a few model architecture breakthroughs that can be highlighted. So in the attention layer, we have flash attention 2, which enable us to essentially spend less memory while training by rearranging the order of operations. And we have a thing called group query attention, where we realize we don't need the entirety of the dense layers. We can remove some of them and get essentially nearly the same quality. As a result, the changes in the attention layer got us into a state where we use less memory. And memory usage is a big bottleneck for train time and also for inference time with these models. We also changed the way we do the positioning encodings. Nowadays, the state of the art is to use position encodings called rotary position embeddings. It's related to the Fourier transform, so you can imagine things rotating around at different frequencies. And the nice property of this positional embedding layer is that it can scale. So you can train it at a certain scale. You can essentially stretch it, then fine-tune it with a larger context length, and so on and so forth. So essentially, you can start with a training set of shorter sentences, which are easier to learn, and then stretch your context length as you are training the model. We also saw reinforcement learning as a more popular final step of training the models. There was a very big change from GPT-3 to ChatGPT, although in most metrics they are kind of the same, but well, the original version of ChatGPT, but ChatGPT was much, much better from a human perspective. So we realized that, okay, we want to have some human information in the loop to get models that are more aligned with what we humans expect. So last year, May last year, I took this screenshot. And in this screenshot, this is a table of human evaluated scores of the models. And according to we humans, the state of the art was a model called GPT-4 Turbo. And we could see here on sixth place, Llama 3, the big version of Llama 3, which was, well, not so far from GPT-4 Turbo. And you could run Llama 3 in a large consumer desktop. It didn't fit in a single GPU, but if you had a relatively powerful computer with multiple GPUs, you could run Llama 3 without needing any cloud services whatsoever. So what has happened since then? I took this screenshot last week. We have in the first place Grok 3, which is a model from XAI. We can see here on seventh place Deepseek R1, which also runs in a large consumer desktop. But we see here on ninth place a model called Llama 3 with 27 billion parameters. And this is a model that actually runs in a single GPU. And it's not a server-grade GPU. You can buy like a 5090 and you can run this model on it. It's an expensive GPU, sure, but you can do it. Also, important detail, this image can handle images. So it's not just a text model, it's also a model that can understand and interact with images. If we go back and scroll down on this list, we can see that GPT-4 Turbo, the one that was in first place a year ago, is now number 50 on the leaderboard, and this was 10 months ago. And there are many open access alternatives, not open source, open access, slightly different thing. So how did we get here? Now I want to present a couple of breakthroughs. It's a very limited selection because, well, we only have a couple of minutes to go through them. But I would consider these to be one of the most important breakthroughs in the last couple of months. I'm going to highlight a few models, such as Qwen2 here, but these are not necessarily the models that introduce the breakthroughs. These are simply popular models where we can see certain phenomena happening. I have references in this slide deck, and I'm going to share the slide deck by the end. So you can follow the reference track and actually find the papers that introduce these techniques. First family of models I want to talk about is Qwen2, which is created by Alibaba in China. And one thing that Qwen2 has that is very, very visible is that it's not one model, but rather a family of models. You have several sizes, and not just the sizes. You have different terminations of the model. So you pre-train it once, and then you do different fine-tuning strategies to obtain different final results for different goals. So you have a model that is good at chatting. You have a model that is good with code, another with mathematics, one that can handle images, not in this diagram because this is from Qwen1 and Qwen2 has more things. The Qwen2 also has an audio model. It also has a model that can do reasoning traces. So they have different terminations for a single large pre-trained run. This essentially with, so most of the money we'll be spending is on the large pre-trained runs. So you can essentially reuse that money for different goals. The second thing that is very visible with Qwen2 is that they train with more tokens at each iteration. And the quality of the data set has also been increasing. So two things at once, more tokens, more quality. So essentially, they have a large data set, and then they apply filtering using the model of the previous iteration. And then they also generate synthetic data using the model of previous iteration. So you can see this cycle where models become better, therefore they become better at filtering, they become better at creating synthetic data. You can create a higher quality data set, so on and so forth. Second family of models I want to talk about today is the Deepseek R1, and this will be probably half of the presentation because they have a lot of things in this model. So in this Deepseek R1 model, the first thing that's obvious is that they use a concept called mixer of experts. They didn't introduce it. It actually has existed for a long time ago, this concept of deconstructing the problem into smaller problems and try to optimize for them. It's a very, very old idea. It is not new. It was not introduced by machine learning, but it is very powerful in the context of language. Intuitively, you can think about it as each expert being good at a certain type of tasks, but in practice, it's not as easy to carve a split between experts. So long story short, you replace this feed-forward layer of the large language models. It is usually a dense layer, and instead of having a single dense layer, you have many, many, many tiny dense layers that you sparsely activate. So in a single forward pass, you only use a small portion of these experts, of these dense layers. So as a result, you get better quality for a same number of active parameters. Active parameters is very different from the total number of parameters. There are two different things. And the metric that they use to justify using mixture of experts is the number of active parameters. If you have a complex training setup or a complex inference setup, the number of active parameters at the end of the day is what actually matters. But if you are a GPU poor person, this is actually very bad for you. So what is the novelty that we can see in Deepseek R1? So these mixture of experts can be seen as this diagram on the left. This is actually a screenshot from the paper of Deepseek V3, which is the base model for R1. And you can see that, first of all, there are a couple of experts on the left that are called the shared experts. These are used at every single forward pass. So we always use these experts. But then we have many experts called rooted experts on the right that are sparsely activated. So you only use a subsection of these experts. You actually have a router layer that is a learned layer that tries to distribute essentially tokens across these experts. Some of them are activated. You pull the outputs of these layers and you send it for the next layers. So in R1, or more generally in large language models, we know that training mixture of expert models is very, very difficult. So if you simply replace your dense layer by this, your training will fail. So as you are starting to train, some experts start becoming better than others. And this routing layer learns, I should always send my tokens to these few experts which are really good. And then all the other experts are not trained. So essentially, you suffer from a thing called routing collapse, because many experts will not be trained in practice. Therefore, they will be useless in the final model. Usually, the strategy to work around this is to use an additional loss term. So for each trained token, there is a loss term that tries to load balance these experts, but this has a drawback. This reduces the quality of the final model. So Deepseek R1 introduced a new strategy where they load balance without actually having a token level loss. So they have a bias term for each of these blue routed experts. And by the end of each training step, which sees many tokens, if a certain expert is used a lot, you increase the bias. If other expert is not used enough, sorry, the other way around. If the expert is not used enough, we increase the bias because we want to use this expert more often. And if the expert is overloaded, you reduce the bias so it is not as frequently used. However, they have a sequence level load balancing loss. So for a given input that you send to the model, they have a loss that explicitly wants the model to learn to distribute the different tokens in a sequence across the different experts. This is essentially, there are many ways you can think about the importance of this, but one of them is at inference time. If you are always generating using the same expert, you can see each expert as having its own queue. So the queue for a few experts will become full, and we'll start seeing more latency. And while for the other experts, it is empty. So you always want to nudge the model into load balance across experts. They didn't find a good lossless solution, so they included this loss for sequence level balancing. Using mixture of expert models has a few challenges. So number one, and the most obvious one, is the large number of parameters, because we have a reduced number of active parameters, but we have a large number of total parameters. In the specific case of Deepseek R1, there are 671 billion total parameters, but only 37 are active for each token, so around 5% of the parameters. This is not suitable if you are running the model on a single GPU, because you can't fit the whole model in your GPU, and it is too slow to essentially move the model between your CPU memory and your GPU memory. However, it's relatively okay if you have a large CPU server, because the model can stay on the CPU memory and goes to the CPU cores without having to be transferred to the GPUs. It actually works relatively well. However, if you have a lot of GPUs, you can do a thing called expert parallelism, where essentially you place different experts on different devices, and therefore you can split the load of having many experts. They are always on memory and each have their own queue, and everything works nicely with expert parallelism. You probably have heard that China has import restrictions from the United States. And in the specific case of Deepseek R1, this was really, really important for the design. So this has a lot of numbers in this table. I don't want you to look at all of them. I only want you to look at the row with the interconnection bandwidth. So how fast can you communicate between different GPUs? And in the case of China, the GPUs that they have on their hands is heavily restricted in interconnection bandwidth. So it's okay if they want to train a small model that fits in one GPU. It's not okay if they have large models that work on several GPUs, because interconnection bandwidth is one of the most important parameters of the hardware to train at scale. And so essentially they have reduced ability to train using multiple GPUs. So modern problems require modern solutions. They have to rewrite the entire model architecture to fit this constraint. So when you use the expert parallelism to distribute the workload of a mixture of expert model, you will need actually a lot of interconnect bandwidth. It is a parallelism strategy that puts a lot of stress in the interconnect memory bandwidth. So they added another detail. At train time, a certain token is limited to visit a limited number of compute nodes. So they modify the routing pass to ensure that each token only goes to at most M devices. This has a nice or relatively nice side effect. If you train with the same device architecture, or well, if you put the same devices, the experts on the same devices at train time and inference time, you will reduce the device interconnection requirements while you are doing inference. So they did this because it was required for them to train with relatively good speed. But if they mimic the same expert parallelism at inference time, they also get benefits, because they essentially have a smaller bottleneck with respect to this parameter. Another detail that they modified in this model was in the attention layer, and they created a modification called multi-head latent attention. So long story short, they added a compression step followed by a decompression step. Usually when we are doing inference with these models, we cache the keys and values from the attention layer. And with multi-head attention, multi-head latent attention, you, instead of caching the full keys and values, you cache the compressed representation of these keys and values. So it results in a smaller KV cache, but it's not, well, it's not no longer a KV cache, because you are not storing the keys and values. It's related to that. And so you have a smaller cache, and you reduce the size of memory transfers. And if this happens to be across different devices, it's really important, because we know that China has import restrictions. This multi-head latent attention, the diagram is this complex thing. So we actually increase a lot of the complexity of this layer. and we are in practice trading memory and memory bandwidth for compute. So we spend more compute, but we save on memory and memory bandwidth. Another important detail that Deepseek R1 introduced was multi-token prediction. So in the outputs of the model, they have one head to predict the next token, which is the usual, but they also have other heads to predict the n+1 token, n+2 tokens. So they want to forecast the full continuations with a single forward pass. And as a result, they actually reported these to help a lot with training under the following rationale. So we want our models to be good at generating completions to the text we send to them. And we are implicitly training the model to be good at generating long sequences. Instead of being implicit and wanting the model to somehow get into this behavior of generating good large completions, why not being explicit about it and help the model learn the full continuation of the sentence, or at least a partial continuation of the sentence. In the specific case of R1, I think they have 4 heads, if I'm not mistaken. So they can predict this number of tokens ahead with a single forward pass. We know that the next token will have a much higher quality than the other tokens because autoregressive generation essentially works better when you have full context of what happened before. And this way you are trying to forecast many tokens ahead without fully knowing if that's the token you are actually going to pick or not, because remember, often you have sampling and other things going on. But with this strategy, we get a much denser training signal. And we also can use these additional output heads for speculative decoding. So speculative decoding is a technique at inference time where you can have your large model verifying whether it would generate a certain sequence or not. And in many situations, or if you have a small batch size, you actually get large speedups when you do this verification as opposed to generating from scratch. The hardware requirements are different if you have a large batch size or a smaller batch size. Many times at inference time, you have a smaller batch size, and this speculative decoding technique is a way to work around it. They also created many hardware level optimizations. Probably the most important one is a thing called dual pipe, which is a different way or a specialized way of doing pipeline parallelism, so distributing the model across several GPUs to train them. And essentially, they have to rewrite the whole thing to hide the communication bottlenecks because of that specialized worse hardware. And they also had many more hardware level implementations. So they, as you can see, they made many changes just to fit with these limited constraints that they have in China. But this is not, I wanted to talk about this because it's not isolated. So if you are doing training in Europe, inter-device connection bandwidth is a very important parameter, and these techniques allow you to alleviate this bottleneck. So essentially, you might be able to get better performance of your training runs if we implement some of these techniques in your model. A very important detail of Deepseek R1 is the synthetic data. So if you read the paper and try to map the entire training process of R1, you'll end up with something like this. So you start with the base model at the top, you do different fine-tuning steps. Those are represented in yellow. You generate some data sets along the way, represented in red, and you obtain certain models represented in blue. So it's actually a quite convoluted process. So let me try to explain it, simplify what's going on in this entire process. So you start with a high quality instruction following data set created by humans that have reasoning traces. So you have a prompt, and then you have a human essentially typing step by step what they would do to get into the answer. You fine tune a model on that data, and then you use GRPO, which stands for Group Relative Policy Optimization, if I'm not mistaken, which is a reinforcement learning technique that is more memory efficient than the others that are popularized. And use this reinforcement learning strategy to create a model that's good with formatting and correctness. You don't care about being helpful. You don't care about it being harmful or not. You just want the model to be good at this step. By the end of this step, you'll end with a model that they call Deepseek R1 0. So it's a model that can do reasoning, and it's a model that is good with correctness. Now, to get from R1 0 to R1, essentially you use the R1 0 to generate a synthetic data set, because remember, it's good with reasoning, it's good with correctness. But you ask the model not to replicate the same type of data that it has seen during its fine-tuning step, but rather generate a lot of synthetic data on more diverse domains. So use your reasoning process in more types of prompts. Essentially, and you use the base model, not Deepseek R1 0, you use the original Deepseek V3, which is the base model, as a judge to filter the data. You're probably seeing the trend that using models as judge is quite important to get quality synthetic data. So you obtain a data set of many traces for different domains, and you fine-tune your base model using this new data set. And after fine-tuning your model with this data set, you also do the reinforcement learning step, but this time also focusing on helpfulness and not being harmful. And as a result, you get Deepseek R1. So if you look into this process, you only need human data in the first step. If I'm not mistaken, you can start, they mentioned they start this process with 20,000 reasoning steps. I'm not confident this is the number. I don't fully remember it, but it's a relatively small number. And from this relatively small number, they can craft a specialized synthetic data set that is used to create Deepseek R1. If you go look into the human annotated leaderboard, there is a significant jump from the base model to R1. So this is actually a strategy that works quite well. The problem with it was that even though they released the model, they didn't release the synthetic data set, and we have seen that is a relatively challenging process to replicate this process. So no, we can simply create R1 at home, even if we had infinite compute. We could, but the process is lightly documented. I'm sure there are a lot of details that they haven't described along the way. To that end, we at Hugging Face have a project called Open R1, where essentially we want to, starting from Deepseek R1, we want to create the data that allows people to create the Deepseek R1-like models. So create the data and the pipeline to essentially do the whole thing. So having public data is extremely important to reproduce results and to advance the state of the art. And because data is very hard to come by, many companies simply decide not to share the data. Yes, they share the model, but you can't reproduce a model of a similar quality easily. There is a lot of data processing going on that you don't have access to. Well, maybe we'll have Deepseek R2 soon. So this is a screenshot from yesterday. The Deepseek team has uploaded a new version of the base model for Deepseek. So they called it Deepseek V30324, which is the date of yesterday. And today they shared a few metrics. So essentially, we can see that this base model, so it hasn't gone through the whole reinforcement learning with synthetic data process. It is already better than a few popular models like Claude Sonnet 3.7 or GPT 4.5 on certain tasks. So maybe we'll have a Deepseek R2 quite soon. The last model I want to talk about today regarding breakthroughs we have seen recently is Llama 3. So Llama 3 is a family of models from Google DeepMind, and it has introduced a few novel things that I want to talk about. So first thing that they haven't introduced the concept of local attention, but they have made good progress using this concept. They replaced the normal attention, which can spend attention to the whole context. They have decided, okay, we don't need all layers looking at the entire context. We can have most layers just looking at the most recent tokens with a sliding window. They started Llama 1 without the local attention. On Llama 2, they had every other layer had local attention with a relatively large context length, but they were more aggressive with Llama 3. So for every 5 local layers, there is 1 global layer. And the local layers can only look at the 1,000 most recent tokens. as opposed to the full context length, which can be 128,000 tokens. So it's a very localized layer. As a result, the biggest impact is that we have a smaller cache. The cache is becoming a bottleneck, so we need bigger and bigger GPUs just to be able to generate text, even if the model stays the same size. The longer we generate, the more memory we need. We are allowing very large contexts, so memory is becoming, the cache memory is becoming a problem, and they have designed these to essentially help with the cache size. We can also have image as tokens. So they have I put it under quotation marks because they are not tokens, they are not discrete integers. You actually use the hidden states of a model that is called SIGLIP, which was trained to align embeddings between text and images. And you use the hidden states with a projection layer as an input to the model. So long story short, this SIGLIP model slices the image. That's why you can kind of think about it as tokens. So long story short, geometry models can accept images as input. There are many models that can accept images as inputs nowadays, and this is the most popularized strategy to convert the images into slice the image and then get hidden states for those slices. Now, geometry, however, popularized the concept of having bidirectional attention for the images. So usually the models, as they are generating, they can only pay attention to tokens that are before the current token. They cannot look into the future. They can only look into the past. That's why it's called causal language modeling. However, they decided to change things up with images. Since we are now representing images as tokens, whenever we can access one token of the image, the attention mask now allows us to access the entire image. That's why they call it bidirectional image attention. The logic is that as soon as you start seeing like a corner of the image, you don't want your model to be limited to the corner. You actually want the model to see the entire image before it can start internally reasoning about the image. Last slide I have for this section is test time compute. You probably have seen this word being thrown around in different contexts. The definition is very loose. I would define it as essentially doing search at inference time. And there are two major ways of doing it. You can do it implicitly, or you can, well, yes, implicitly in the sense that you can train your model to generate more or less tokens depending on the complexity of the task. So if you use Deepseek R1 and you ask him like a relatively complex question, you probably see that it generates a lot of tokens because it was trained to behave this way. When it sees like complex tasks, it generates more tokens to reason about the problem until it replies with the final solution. But you can also be explicit about it. You can just grab a random model and try to force this behavior into the model. You can essentially control the decoding loop of the text generation and force the model in many different ways. This is an extremely open-handed topic, but you can force the model to think more about it. A very simple technique that works relatively well is to inject weight, the word weight, by the end of generation. And then the model continues thinking because it thinks that there is more to the question. This technique is called budget forcing, but there are many different things you can do about this. So to end this presentation, ideas for the next year. Again, this is a very, very, very limited set of ideas. There are many more out there. We can see with a model called 5-4 multimodal that we are seeing models that can accept as input more modalities. So this 5-4 multimodal model can accept images, text, and audio. And at inference time, depending on the different, if you pass it image plus text, it will use a set of weights. If you use image plus audio, it will use, well, the same base weights, but with a different low rank adaptation. So the model, you can see the models as changing a little bit depending on the modalities you feed as input, but they share a lot of parameters. So the core parameters are trained together. You also have a model from Deepseek called Janus. This model does image generation using tokens, and this time is using actually discrete tokens. So this Janos model can accept both images and text as input, and you can ask it to output text as a normal text generation models, but you can also ask it to generate images. It will actually generate tokens, discrete tokens, and then they have like a final module that converts these tokens into an actual image. It's not as good as diffusion models, but the quality of the images is not that bad. It's improving very quickly, iteration after iteration. And maybe it's another way we can train everything together in a single model. Last item, I think this is the last one, is a model called Llama, which does diffusion for text. Personally, and this is a very personal opinion, I don't think diffusion will be the best solution to generate text. Essentially, the way this works is that you start with the whole mask test. The whole output sequence is masked, and it will try to unmask tokens at each iteration, and you can remask them again if you want. But it's very hard to generate a coherent sentence if you try to do it all at once. So there are a few follow-up papers that interleave diffusion with auto-regressive strategies. So they do diffusion on a few tokens, and then they send it to the model again, and then they diffuse a few more tokens. But long story short, what I want to talk about, why did I want to bring this up? Diffusion is much faster than autoregressive generation. So this is an interesting research direction. And I believe the worst case scenario, it will be good for smaller models because it is much faster to use than autoregressive generation. And that's it for today. Thank you.
Great talk. Does introduction of GRPO means RLHF is dead?
Sorry?
Does introduction of group-related policy optimization means we can scrap the reinforcement learning with human feedback?
You need the cold start data. So the first set of data set to models are not, let me put the right slide on. Models are not good at producing reasoning traces, or at least with the data sets that we are training the models with at the moment. So we need to force this behavior into the model. And therefore, we need some human data to create a data set to force this behavior. Maybe in the future, with this whole loop, we can essentially bootstrap the whole thing. We have a decent model, we generate a synthetic data set with reasoning traces, and then we train a slightly better model which generates a slightly better data set, and so on and so forth. So I want to say that yes, we will be able to remove humans from the loop, at least with respect to data, but we will be the ones evaluating the models at the end of the day. So we will be in the loop, at least in that part.
But it's great news that we put people at the creation of data set, not at curation of the wild data coming from uncultured model.
Sorry, before we continue with questions, this last slide, the QR code, is a link for this slide deck, if you want to have this slide deck.
Okay, any more questions?
Can you go to the first file? You have the mixture of experts. It's kind of a detail. So
this one?
Yeah, that's one. So if the ones that are called the shared experts, if they're not gated, in what sense is that a mixture of experts? And why is it different than just one expert, one big expert?
I don't know the answer to that question, because yes, they could be a single dense layer, because they are not gated, therefore they are trained with each token.
Okay.
So I don't know the answer to that question, sadly. In my head, I agree with that rationale to use a single dense layer for the shared experts.
Okay, thank you.
Sorry, actually, I might know a reason. It might be easier to distribute them across devices. If you have experts with the same size, it might be easier to distribute them.
So it's a practical reason. Yeah. Thank you.
More questions? Yes.
So great presentation, really insightful. So I was thinking about the things that you mentioned for 2025, 2026, that mix, that, use, some of these proposals are based on adding more modalities. And I think this brings an opportunity, which I think is models are not doing yet, which is not just thinking with text, but thinking in those other modalities as well. For example, visually, right? Do you have any thoughts about what could be the potential in this direction?
Physics AI is a word that gets thrown around since last month at least. It dates, it's much older than that, but Cis Lecan brought it up. I agree with the concept from an abstract level, but I don't know how to implement it. So I honestly, I don't know, in addition to providing more data to the models, maybe annotating them somehow, giving like simple examples, explaining the physics behind an image to see if the model can start learning about it. But honestly, I don't know. I have very limited ideas there.
My question was more like, for reason. So right now, these models like R1 and so on, they reason over text. So they have these tokens that are just text. Of course, the physics are important, and there's lots of things that could be done there. But even at a shallower level, we can also think about models that are able to generate images and then operate over those images as they are generating the final answer to solve problems that can be more complex, even without modeling the physics explicitly. That's more or less what I was hinting at.
That reminds me of how some diffusion models work, where they do diffusion in the hidden state. They don't do the diffusion on the actual images, which was the original process. So maybe we could have something about it. Like text generation has one, in my opinion, frustrating part, where we collapse the output distribution of the model into a single discrete integer. And maybe if we don't collapse it, we could do better things.
Any more questions? Yeah. If there are questions at home, you can also write it in the chat. Okay, so maybe let's give another round of applause. Great presentation.
Thank you so much. Thank you, everyone.